Hello everyone, in this video we'll find the expansion coefficient beta and the compressibility coefficient kappa with the Berthlat state equation. Let's get started. The Berthlat equation is the expression that we have over here. Notice that this expression is very similar to the Van der Waals equation. The only difference is that we have a d factor over here. But that d factor will make that we have some additional operations in order to calculate the coefficients beta and kappa. First, we need to solve this equation for p in terms of t and v, like this. And we must remember that the coefficient beta is equal to this expression and kappa is this other expression. So let's calculate this for coefficient beta. In order to do that, we need to know what is this derivative. We can find that we can solve an expression for the volume for this state equation, but we notice that it's almost impossible to solve for the volume because we have a cubic equation, and a cubic equation it's impossible to solve for a specific variable. So we can also think that it's possible to use this reciprocity relation in order to compute a easier derivative and replace it in this equation and find the volume. But in this case, if we try to solve this derivative of t with respect to v, we'll notice that it's very difficult also to compute and solve this equation for t. So if we can solve for t, we can use this expression. So in this particular case, this expression can be possible to use it. To solve that problem, we can use this other expression that it's very known in thermodynamics. The derivative of v with respect to t times the derivative of p with respect to v times the derivative of p with respect to v is equal to -1. With this expression, we'll solve for this derivative, that is what we're looking for. So if we do that, we'll get this expression. So we only have this expression that is multiplying to the other side divided. Exactly like this. In this expression, we can calculate this derivative easier. But for this expression, it's a little bit more difficult. But for this expression, yes, it's possible to use a reciprocity, a relation. And in this case, we have these terms. The derivative of p of t with respect to p is equal to 1 over the derivative of p with respect to t. If we replace this expression over here, we'll get the next equation. So let's go to solve this fraction and we'll get finally this expression. So just that it's dividing can pass in the top, multiplying with 1, and we'll finally get this expression. Those derivatives are too much easier to compute than only this. So when we calculate this derivative, we'll replace it in this equation, and finally we'll get this derivative of v with respect to t. So let's get to calculate this first derivative. In order to do that, we need to the state equation, and let's go to derivative with respect to t. In this case, v it's a constant. We can solve this derivative using the rules derivatives. In this case, that we have already this equation, we can replace this term with help with the original equation. So let's go to solve r over v minus b like that. From this equation we can get this term and we can replace it in this derivative in order to get this other expression, making step by step all this operation. We can get these other terms and we need to sum them. We'll get this expression. If we sum these fractions, we'll get this other term. And let's go to compute the other derivative with the original state equation, but in this case will be with respect to volume and t constant. If we get the derivative, we'll obtain this expression, and likewise the other term we can replace RT with help the original equation. If we take the original equation and solve for RT, we'll get these other terms, and we'll be able to replace it in our derivative. If we do that, we'll get this expression. So in this case, we just need to simplify the operations that we have in these fractions. For example, in this case, we have this term that could be simplified with this term with 1 power over here, and solve that multiplications and the sum of fractions like that. In this case, we've simplified this term. So now let's go to sum these fractions like that. In this case, we've only amplified this fraction in order to sum in a direct way. This is the sum of this part, and simplifying a little bit more. In this case, we're only multiplying 1 times this term and v minus v times this term, and we have all this term that we have between brackets, and this other term it's exactly like that. So we can change the terms. First we'll start with the positive term and next the negative, and let's go to sum these fractions, and we'll get these terms over here. So now we know what this derivative is and what this derivative is. So let's go to replace it in our derivative. And for example, in this case, the parcel of t with respect to t is this expression over here, and the other part is this expression over here, right? It's the expression that we just calculate. So now we just need to solve this fraction. It's a division of fraction, so it's really easy to solve it. We'll get this other expression. In this part we can simplify some terms. For example, this t can be simplified with this t squared, v cubed can be simplified by v squared, and finally we will get this expression. We know that theta is equal to this term. We can replace this derivative because we have it over here. So let's go to replace it. So now we notice that we can simplify this v with this v, and finally we'll get this expression over here. So now we have first this expression. This is the first coefficient. Let's go to compute the next. The next coefficient, the steps are pretty similar, but we have an advantage. For example, we know that kappa coefficient is equal to this expression, but we already know what this derivative is. We've already computed with this expression before. We know what is that derivative. That derivative is this that we have over here. And we can replace it in here. And we know that the derivative of v with respect to p is equal to 1 over this derivative, but this derivative is equal to all this expression. And we need to solve this expression, and we'll get these terms. We can replace it in our original expression for kappa. Kappa is equal to minus 1 over v times the derivative, but the derivative we already have it. It's all this expression, and we can simplify some terms. In this case, v can be simplified with the bq, and this minus is introduced in the denominator. So finally we'll get this expression, and in that way we found the terms for beta and kappa, the expansion coefficient and the compressibility coefficient. And that's it for today's video. Thank you very much for watching, and see you next time.